Delightful to be here to talk about one of my absolute favorite subjects, life on Earth. And as was mentioned, after 42 years inside NASA, I've accumulated a lot of secrets. In fact, I probably made a few of those. And so I brought NASA's secret files with me. So let me get them out. Here they are. Let me open them. All right. So that enables us to talk about any aspect of where we are in the process of searching for life beyond Earth. It's really an exciting time for us because of all the assets that not only we've deployed across the solar system, so we can understand what our solar system is about and where the life has been on other planets, not just this one. We have to know those things, so we want to understand the evolution of our solar system and use that knowledge as we look out into space looking for exoplanets, those planets in particular that are not just Earth-sized, but Earth-like. So in 2006, I became the head of planetary science. Very excited about that. And I asked my astrobiologist, NASA's planetary program, biology theme, which is really all about looking for life beyond Earth. I said, give me a definition of life. You know, now I didn't tell her this. This was Mary Wojtek. I didn't tell her at the time that I was thinking, oh, we'll go out and build some instruments and fly them and go find it, right? Because that would have really turned her off. So she went away and it held a group of scientists together. And after a while, and that must have been at least 6 months, came back to me and said, I have the answer to your question. Now, she answered it in a way that doesn't mean life as we know it, but a general definition of life. And so life has 3 attributes. Okay, she told me it metabolizes, it reproduces, and it evolves. And the metabolism process is very important to understand. It means you take in food with a solvent, in our case it's water, separate out the nutrients that you want, and then the water is used, of course, or the solvent is used to eliminate waste. Now, she told me this, and she was just absolutely delighted they've got it, and now, you know, now they can move forward. And I can't tell you how depressed I was. I mean, how are we going to make a measurement of evolution, let alone, you know, reproducing? And metabolism is also a tough one. Other than the concept that you need not only the certain nutrients, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, okay, everything that's between my 2 fingers, but you also need some sort of solvent. All right, so with that, we then began the process of following the water. Where in our solar system is water? The bottom line with that is, what's happened on Earth may have happened in other places. So the more we understand the evolution of Earth and how life came about and how it's evolved, the better off we're going to be in terms of looking for life beyond Earth in exoplanets. Okay, so this is also an important input to life, and that is the ingredients. Once again, we need the water, we need the organics, okay, carbon, nitrogen, oxygen, hydrogen, phosphorus, and sulfur. We need energy. You know, you've got to be able to have a certain temperature range where those things can come together, chemically interact. Life can produce a variety of organic compounds that it needs on its own for it to evolve. But the one thing we don't talk about much that's extremely important to understand is time. We need the time for the environment to change gradually into something that's conducive for life. So we're going to tackle that a little bit tonight, more so than anything else. So the first time scale we need to know about is the sun. All right, the sun provides us heat. That's the energy and the energy source that we need. And the sun has started its processes 4.5 billion years ago. It hit what's called, for the astronomers in the crowd, the main sequence. Therefore, it begins to generate helium in its nucleus by bringing together hydrogen and creating helium. And of course, for those here in the Institute, the most important equation relative to that is E equals mc squared, okay? 4 protons weigh more than a helium nuclei. And if you crunch them together, the delta M, the mass, produces energy, and that's what happens in the interior of the sun. Well, when the sun hit the main sequence, that's down here at the bottom on the graph, and then it goes up over time with the age today shown in the dashed lines. The sun is 25 to 30% dimmer then than it is today. And it's only going to get hotter, all right? Now, climate change, a lot of people talk about climate change. The climate change that we're talking about is not being induced by the sun because that curve is so slow that climate change is happening on hundreds of years today and not 100,000 or 200,000 or a million years, all right? So that's not what's happening. Another thing that we knew by looking at other G stars, our sun is called a G star. By looking at other G stars, the younger they are, the more active they are. And the activity is measured by sunspots. These are really big magnetic structures that as they collide, they produce magnetic bubbles and they blast out a chunk of its atmosphere out into space, and then it hits a planet and it can strip an atmosphere. If it hits a planet with a magnetosphere, it can get pushed away, but it still can be powerful enough to strip the atmosphere because the magnetosphere can't respond fast enough and with enough power to be able to push these coronal mass ejections away. So the early sun was a really big problem, all right? So we had to figure out, well, if life started early on Earth, it had to survive this really intense period. Carl Sagan coined the term faint young sun. If life started many billions of years ago, when the sun is fainter, how did we end up having an environment where life could exist? Okay? Now, another construct that astronomers use today is called the habitable zone. Okay? It's an important construct, and it's the start of a really important idea. And what this means is, as the sun emits light, of course, because you come to the light source, you have more intensity of light. And as you move further away, that intensity drops. And so there's a region away from the sun for which the light intensity is just right on a planet about the size of the Earth that allows it to have water in its 3 phases. Not only ice, but vapor, and most importantly, water. And that area is called the habitable zone. So when you take the idea of the faint young sun that Carl coined, and then you look at how the sun has grown in intensity, you see the habitable zone was close to the sun, and then over time it moved out. Early on, Venus was in a nice part of the habitable zone, but Earth and Mars were not, okay? The real thing that we need to look at when we talk about the evolution of our planets and whether life could have existed on them in the past is really what we call the habitable state, okay? What makes a habitable state is an environment where the temperature is such that you can have water in its 3 phases, you can have all the organics you need, and you have a long time period in that habitable state for life to start. So here is a depiction of the habitable state and where the planets are today, okay? So we see when it's too hot, Mercury and Venus are not in the habitable state. Earth is well situated in the habitable state, and Mars is too cold. It's also not in what we would call a habitable state. Now, what we're going to see in this lecture over time is how these planets evolved and how they move in and out of a habitable state. Because when we do that, we then can zero in on that planet to understand its history at that epoch to determine if it had life. All right, so let's look at Mercury. This is Mercury. It's much bigger than the moon, but not as big as Mars. It's our smallest terrestrial planet. It looks like the moon because it has no atmosphere. It's marked by enormous number of impacts. The coloring we see comes from the messenger observations of the moon in a nice wavelength, infrared wavelength. And what we see are the bright areas. The bright areas, of course, many of those indicate volcanic activity. So the moon has partially resurfaced itself. No indication of plate tectonics. No big modification of the craters like a big atmosphere would have. And so what we can say then, the evolution of Mars from when it started to when it is today to what it's going to be in the future is it's never going to make it, okay? It's on a dead-end evolutionary track. Well, what about Venus? Okay, Venus is our next terrestrial planet. And of course, Venus in particular, early on, when what we did in science and science fiction was look at the planets from telescopes. This is before the space program. Everything we knew about planets comes from telescopes. It really looked, we see clouds, we saw, what would be considered weather, perhaps. And so a lot of the science fiction writers were talking about Venus as an abode for life. But what did we really end up knowing about Venus in the space age is this. Today, the surface of Venus is hot enough to melt lead, okay? And the atmospheric pressure is 90 times our atmospheric pressure. To receive that amount of pressure here on Earth, you have to go into the ocean more than 1,000 meters. Crushing depth. This is why it's always been so very hard to get down on the surface of Venus and really take a good look at it. Well, the planetary scientists in the 70s, late 70s and into the 80s, as data was coming back from the Soviet Veneras, this is the bathtubs that were landing on Venus, making the measurements that allowed us to understand its atmospheric structure and what was happening down on the surface and making those wonderful measurements I just told you about. Well, they were taking their codes, trying to understand how come Venus is so hot. It's that way because it has a runaway greenhouse effect. That's all about greenhouse gases, and this one, the dominant one, is CO2. And that CO2 allows light from the sun at all wavelengths to come in, heat the surface, but then as the surface radiates back into space in the infrared, the CO2 doesn't let it out and it just heats up. Very similar to what happens in your car during the summer. When you walk in, that window allows the light from the sun to come in, but the heat of what's happening on your cushions is radiating in the infrared, and that does not go through the window. It's not transparent in the infrared. So it just heats up. So what we knew about Venus until probably in the last 8 years was we didn't know much about it. There was an unknown evolutionary part, and then we knew that it had a lot of volcanic activity. Some of these areas on Venus were really hot, and when we mapped them to radar images of Venus, they were always on these big, huge hills, which we now know are volcanic domes, okay? Venus right now is also quite volcanically active. Now, as I mentioned, we did do radar with Magellan in the 70s to get through the clouds, get down to the surface, bounce those radio waves off, and then figure out how far away that surface is from the spacecraft so we can create a map like this. Now, this is a topology map, colored, for which the reds and the whites are the highlands, and the blues and the greens and the yellow are more lowlands, with the blues at the very bottom. We also made one really important measurement. Venus has water, and we can make a measurement called D2H, which is deuterium versus hydrogen. Now, water is H2O. That means 2 hydrogen to 1 oxygen. But there's also a variation of hydrogen called deuterium, for which you have a proton nucleus and you add a neutron. Okay? So still hydrogen, but it's heavy hydrogen. All right? And that's called the D. So you can have DOH or DDO. Okay, so deuterium then has to be considered an important element of water. And if you have the same D to H ratio, you can go right out here to the pond or the ocean, grab a bunch of water, look at the D to H ratio, you know what it is, and you apply that to Venus, it means you're going to have to put an enormous amount of water on its surface. So when you put an enormous amount of water on its surface, it actually becomes a blue planet. Now, this is early on in its history. So we're starting to fill in that area where we didn't know what was happening on Venus. So early on in its history then, how did Venus actually keep that water from being evaporated away? And then the solar wind rips that oxygen apart and down the heliosphere it goes, never to return to Venus, and the water evaporates away. Well, it turns out, because Venus is such a slow rotator, clouds build up at what's called the subsolar point, reflect the light, and Venus is a blue planet for a long time. And in fact, it's probably started into this process of losing its water 800 million years ago. So from a planetary perspective, it could have been a blue planet for more than a few billion years, okay? For more than a few billion years. Now, that tells us it had an opportunity, because we know, we believe as a terrestrial planet like Earth, that it probably had all the right material to be able to generate life, and it had plenty of time, but that's no longer the case on the surface. And so consequently, Venus came into a habitable state and then left it. Okay? But because we know what Venus looks like today, in contrast to what Earth looks like, those are also important Rosetta Stones to be looking for other exoplanets that are Earth-sized. Well, let's talk about Earth. And Earth's history is pretty fantastic. It's very reachable for us because we can go and age-date rocks. We can see fossils. We can look in the rock record, and we can look at how, at what era life started, what kinds of life there was. And life, of course, became very simple at the beginning. We believe about 3.6 billion years ago, maybe 3.8 billion years ago, life started on Earth. All right? Now, if Earth is 4.6 billion years, it took a little while, that's the time part, before it kicked in. Now, that was simple life, all right? And that simple life had to evolve, once again, over a long period of time into more complex life. So what's complex life? If you look at your body, we have all kinds of different cells: heart cells, liver cells, brain cells. The more different types of cells we have, the more complex we are, okay? So you go from single or multiple cell life that's simple into more specialized functions and complexity. Those cells got together because it might have been cold outside, and then the outer cells, well, they began a process of evolving so that they could keep the inner cells warm, for instance, as an example of how cells begin that specialization process. The really interesting thing, of course, is the life that we really know, the complex life, is actually fairly recent on Earth. It's only about 500 million years. And in that 500 million years, the last 500 million years, there's been about 5 mass extinctions. Now we're on the hunt to what really is causing those extinctions, because if we had extinctions on this planet, what were the conditions? Were they local? In other words, what was happening on Earth? Maybe it was volcanic activity, maybe it was something else, maybe it was asteroids hitting us, and that's certainly the case for the loss of life 65 million years ago when the dinosaurs died. But in reality, there may be other things happening to the entire solar system as it moves around the center of the galaxy that affects everything. And we're just coming to that realization. And so we have a lot to learn on what these extinction events are really all about. But from that concept, we can begin the idea that the evolution of the atmosphere must have occurred. And I mean radically huge changes. Started out with a lot of carbon dioxide. And since that's a wonderful greenhouse gas, that allowed the Earth to stay in the habitable zone, habitable state early on when it wasn't in what we would call the habitable zone. So the atmosphere and how the atmosphere evolves now is one of the key things to try to understand to allow it to be in that habitable state. Well, 2 billion years ago, a huge change occurred when we had cyanobacteria eating that carbon dioxide like crazy and emitting oxygen, all right? So this simple life just allowed a huge change in the atmosphere, given enough time to do so, all right? And so that ended up being the big thing that allowed us then to evolve into using oxygen as we have today. Now, the top greenhouse gases on Earth, the very top one is water vapor. The next one is methane, and then CO2. So when we talk about climate change today, even though a small amount of CO2 ends up in our environment, it changes that distribution. The ocean heats up, more water vapor is emitted, and the temperature increases. And so a small input produces a larger forcing function that's changing our climate. Now, the Earth continues to go through its own evolution climatically. You can see it here. So if you ask a planetary scientist about, climate change, they're going to say this: the climate has done nothing but change. Life has to evolve as it changes. And as it's evolving, it has thousands of years, because these changes, given a nice environment that we've had, okay, have been so gradual that life then becomes able to live in an ever-changing climatic environment. Well, when the climate change, instead of thousands of years, starts being hundreds of years, then that tells us that our technology is enabling the climate to change, and we have to be cognizant of that as we then live and work in the future. That brings up one important thing. Can we see technologies of other planets changing their climate too? And we call that a technosignature. So not only are we looking at biosignatures, like methane, all life emits methane, and we call that a biosignature, but methane can also be generated abiotically with processes that don't require life. So consequently, you want to be able then to look at these atmospheres and begin to determine a suite of information, not just that you found a biosignature, but what is it like in that environment, and is there a solvent? Is there all the other material necessary to make life and make it complex? And is there technosignatures? All right? So these are the kind of things that are folding into our thinking about how to look for life beyond Earth, because we're really taking a good look at life here on Earth. So here we believe are the spectra. These are of the Earth at various stages. These are important to note, because when we finally get to the point where we're looking at spectra of planets that are Earth-sized and have an atmosphere, this will sort of be our Rosetta Stone. This will tell us where those conditions are such in the history of the Earth, and therefore whether it has complex life or starts to have it or won't have it at all. Well, one of the most important things that I have to tell you about is the early evolution of the Earth, because the Earth and the Moon are intimately related and produce an enormous effect that keeps the Earth uncommonly habitable. And so it starts out this way, 4.5 billion years ago, as the cloud that we're in begins to collapse, the central place where the sun is gathering more material, and angular momentum in this cloud brings it down to a pancake, and planets get created. They start accreting material. They create these bodies from dust from other stars that have gone through their evolution, blown away dust and blown into these clouds, material that it then can freeze, that then can collide, that then can create bigger and bigger objects. So 4.5 or so billion years ago, the Earth collided with another planet. This is the proto-Earth, and this planet is about Mars-sized. So that means in our orbit, multiple objects are being created. And then this planet, we call Theia, planetary scientists call it Theia, slammed into the Earth. Now we can computerize this and model it. And so here's what the model tells us of a body the size of Mars hitting the proto-Earth and creating the Earth and the Moon. So you see the impact is enormous. Theia is totally destroyed. Parts of the Earth and parts of Theia are shattered everywhere. And then it begins to coalesce and come back together. And it will, because the Earth is the gravitational attractor. So here's what it looks like at a snapshot, where you have the very hot proto-Earth gaining more and more material. And then there's an area around the Earth called the Roche limit. Sorry, Roche limit. I like to call it Roche, but it's called Roche. So why is that important? Well, it's an area where if you have a large body that's trying to accrete, it's so close to the planetary body that one side of it gets attracted, and more so than the other. So it's really hard to come together to create an object. Outside this limit, you can do that. Now this limit is about 3 or 3.9 Earth radii away from the Earth, okay? So it's pretty close to the Earth. So inside the Roche limit, everything collapses to the Earth. Outside, everything can accrete, and it forms the Moon. Now, yeah, you can think of Saturn. Saturn has rings, okay? Well, those rings are on the way out, all right, because they'll eventually fall into the planet. Here is the Earth and the Moon after the epoch of collision of Theia with the Earth, and this is what we see. 5-hour day on Earth, the Moon 3.9 Earth radii away. All right, now that's unbelievable. Can you imagine if you could actually stand on the surface? I wouldn't recommend it. Stand on the surface of the early Earth, which is enormously hot, looking up and seeing a moon 16 times bigger than it is today. Well, the Moon turns out to be moving away from the Earth. And as it does that, the Earth is going to slow down. And how we know this is not only was it theorized, because it's all done with math. Okay, you got to have math. Right, Ed? Yes, right. So you have to realize that as the Earth moves away, conservation of angular momentum slows the Earth down and creates a nice milder day, and the Moon moves 1.5 inches a year. We knew this from the Apollo program. We put retroreflectors on the moon. Every year we fire lasers, hit those, the light goes up, comes back, we measure that, and knowing the speed of light, we can determine the moon is still moving away from us, okay? Okay. Now, another thing that we found out, so right now it's at 60 Earth radii away. 60, started at about 4, 3.9, 4, on that order, Earth radii away. It's 60 Earth radii away today. We brought back rocks from the moon, and a lot of them. About 840 pounds worth of rock material. And in that set, we recognized that so much of it had a remnant magnetic field, which means that somehow when that rock was created, whether it was an impact, melted the rock, and then the rock solidified, and then the domains of all the atoms sort of line up because it's of a magnetic field that's pervasive in that area, or it's magma flowing out onto the surface and that rock cools, we end up with a permanent magnetic field in these rocks, and that tells us that the moon had a magnetosphere. All right? Now, why is that important? If you want to push away the solar wind, the best thing to have is a magnetic shield at a time when the sun is really active. And so a lot of modeling's now been done for which you can see the Earth and the moon and their magnetospheres, and they are intertwined, and the moon is running block for the Earth. So during the time of the active sun hammering the Earth with coronal mass ejections, it's also hammering the moon, and the moon is helping keep the Earth's atmosphere. Earth's atmosphere is growing because the Earth is outgassing. Well, so is the moon. Impacts that are occurring on the moon are bringing up magma and then solidifying. And with that comes an extensive amount of outgassing. And we estimate the moon had an atmosphere probably twice that of what Mars is today. And it had it probably for anywhere from 100 million to maybe 150 million years, while it still had its magnetic field. Well, the core of the moon eventually slowed down. The moon becomes tidally locked, and it loses its magnetic field, and the sun just strips its atmosphere away, okay? And when you look at the moon and you see all these pot marks, for every one of those, 20 of those, that size, has hit the Earth. But we don't see them. We see some remnants of big impacts, but because of our atmosphere, because of our oceans, because of our plate tectonics, they're virtually eradicated. Bottom line is, our moon has really helped us be habitable, be in the habitable state for a very long period of time. Its magnetosphere has protected the Earth in the faint young sun period. It's stabilized the Earth's spin axis, okay? The Earth is not spherically symmetric from a gravity perspective. It actually has more mass in the southern hemisphere. It should be laying down on its side as the sun pulls on the Earth and pushes that heavy mass towards it, okay? So it doesn't. It doesn't. So our rotational axis has changed from 24.5 degrees to 22 degrees. Okay, so that just a little bitty change that actually wreaks havoc on our climate. This is called one of the Milankovitch cycles. And so, those people that are studying climate will know about the Milankovitch cycles because that is the underlying process that changes the climate here on Earth. You have to know the baseline before you can figure out what the anthropogenic changes are that are going on. So it stabilized our axis, really great, held it there. Creates a 24-hour day, also quite nice. Why is that important? Without the moon, the Earth would be nearly tidally locked. All right? So our moon is tidally locked. We see one side all the time. Now it's completely tidally locked. But in this case, we'd be about 70% tidally locked. So one day on Earth might be 270 days long, 280 days, something like that, okay? That's not conducive for life, at least as we know it. All right, so the moon has really helped us. And it causes tides. And the concept of life here on Earth is, well, it probably started where there was a lot of water. We needed that solvent, probably in the ocean, and then migrated to the land. The first type of life that we see are microbial mats called stromatolites, and they're on the shoreline, okay? So the concept that life started perhaps in the ocean and moved to the land is still a very viable start of how life might have occurred. So what do we have? Well, the Earth got into a habitable state pretty quickly, stayed there, but it also went through two huge episodes we can see in the rock record. We call those snowball Earths, where the Earth got really cold, and I mean globally cold, such that ice formed over most of the crust of the Earth. But it popped out of that, and it came back into that, and it almost came out of a habitable state completely, okay? So by studying the Earth and how it has evolved over time, we're now going after, well, how did that occur? What are those all about? Will they occur again? And of course, what will happen to the Earth over time is it will become more Venus-like, and will pop out of the habitable state and go into an area where it's too hot for life. Well, let's talk about Mars. Fabulous planet, and it has no big moon. It has two small moons, okay, but they're on the order of 25 to 30 kilometers in size, and they're not really doing much to the planet. And so its axis is going to be affected by the gravitational pull from the sun, because Mars, too, isn't spherically symmetric from a gravitational perspective. It has more mass in one hemisphere than another. And so it goes through these huge changes in its rotational axis angle, and we call that obliquity. And as you see, here's the Earth's from 22 to 24.5 degrees, hardly any change. But Mars goes from 15 degrees to 48 degrees. Huge swings, huge swings. Okay, so the climate change on Mars must have been enormous over these time periods. So we had put together an understanding of what's happening on Mars over time, okay? So here now, from 4.6, when the sun hit the main sequence, up to today, we know Mars was a blue planet. Wow. It had plenty of water. 2/3 of its northern hemisphere was under water by more than 1.5 kilometers. All right? Plenty of water early on in its history, just like the Earth was. They weren't in the classical habitable zone, but they were in the habitable state, okay? Because the greenhouse gases really made the difference. And so now Mars has lost its surface water, and it's moved into an area of a cold desert-like planet. Now, that atmosphere has been withered away. It's been withered away because Mars had a magnetic field, but somewhere along the line, probably 3 billion years ago, it lost it. And when it lost its magnetic field, it also breaks the water cycle. Water cycle is you have an ocean, evaporates, transport, rain, okay? And that's a nice cycle. I'm oversimplifying it, but the basic idea, during that evaporation process, the oxygen and the hydrogen get separated. Oxygen actually then in the higher part of our atmosphere gets stripped away. And from MAVEN, this is the MAVEN spacecraft, as it orbits Mars, it sees streams of oxygen coming off of the planet, all right? Still, part of the reason why is Mars's atmosphere is humid. It actually has a fairly high humidity. We also know that Mars has an extensive amount of water, but in frozen form. Now, when it had plenty of water, it didn't have plate tectonics. So that water seeped into the crust and is there.
We believe it has underground aquifers, and we found at least one huge reservoir of water, maybe many kilometers below the surface. All right? So there's some sort of liquid water underneath the crust of Mars. Now, for us, plate tectonics are stuff for which one landmass moves underneath another. You melt that, and the water comes streaming out. You end up with water vapor like crazy. So you really have a cycle. Mars didn't have that. So once it gets in the crust, it's going to stay in the crust. Now, for us right now, that's a good thing, because indeed, if we're planning to have humans to go to Mars, water is going to be an important resource. So here is also a Mercator projection of Mars, where what we're looking at is colored the topography. So the reds and the whites are the highlands, and you can see there's volcanic activity all over the place on the left. And then you can see the lowlands, huge craters like Hellas Basin. And you see the northern hemisphere is very low because it's also blue, all right? So this is where most of the water is going to be, in these blue areas. And so the ancient shoreline of Mars is going to be along this green to yellow, okay? And that's where you see a lot of our rovers. We're running around in regions that are the ancient shorelines of Mars. In fact, some of our high-resolution observations of Mars are really exciting because we can tell there were tsunamis. Okay, isn't that fascinating? Huge walls of water hitting the shore, going up the mountains, grabbing boulders, and then laying them nice and neat in a row on the shoreline. Okay, so this must have been a fantastic place early on in terms of its dynamics too. Well, unfortunately, most of these have come and gone, and the two that are working are Perseverance and Curiosity, for which I had a huge role to play at NASA headquarters, and I'm really proud of those two missions because they're going after the habitability of Mars. So after we landed Curiosity in this huge crater called Gale Crater, you can see the central peak of the crater is right there. On the opposite side that you can't see is the rim of the crater, and that rim has been broken, and the ancient sea poured into this crater, filled it full of water. And then over time, as that water went down and down and down, and the silt in that water, because it's still, or mostly still, went to the bottom, you can see this looks like an ancient riverbed all over the place. So it's got some really great features about it. These are the first two holes we made on Mars with the Curiosity drill. Now the drill is like a straight screwdriver. It drives itself into the ground, pulls out, turns a little, drives itself again, turns a little, drives it, and it does that. Percussive drill just grounds up the rock and the sediments. Then we scoop that up and we bring it in an instrument, several instruments, and then we look at its mineralogy and we look at its composition. And overall, here's what we find. It has carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Sounds great. The soils have nitrates in them, great fertilizer, and they're moist. And Mars itself is humid, all right? So this is really allowing us to think of Mars in its past must have been in a habitable state. Now, Mars has other fabulous features about it. One of those features is that it emits methane. This image was done by ground-based telescopes in the early 2000s. It's a very controversial image because it shows the areas where huge blooms of methane were occurring on Mars. And if you've got telescopes on Earth, you're looking through methane to see methane on another planet. Really hard to do. And you got to do that as the planet is moving quickly, because that spectra then changes ever so slightly due to what's called the Doppler shift. You have a beautiful train station here. I came today over the train station, and I could hear the whistle from high to low as it moved by. And that movement allows scientists then to see the methane at a slightly different wavelength and know that it's methane. So this is a very controversial observation, but we now know it's true because our rover Curiosity sat on the surface and measured peaks of methane. It was leaking right through the soils, okay? Now methane actually, once it gets released in the atmosphere, doesn't stay there very long. Even our methane today, which gets released in the atmosphere, doesn't stay very long. It's a chemical reaction and with sunlight that breaks it up. And so what's happening on Mars is this is real-time stuff, you know? Whether it was generated recently and then emitted through the ground, we don't know. Whether it was generated in the past and then held underneath the surface, and some surface process let it go, we don't know. And whether it's actually methane associated with life, maybe living in the aquifers, or an abiotic process of molten material with water and olivine creating methane in that interaction, we don't know. All right? But if there's life on Mars, this is a great tracer. We know where it's at. It's in the ground. So as we now know, as the conditions get tough for life on a planet, it moves into the rocks. Now, we found that out here on Earth because the astrobiologists also in the mid-2000s looked for life below our feet. What we wanted to know was how much life is below our feet, you know, and after several years of research and analysis, they came back and said, there's more biomass below our feet than all the mass of life on the Earth, and even add the oceans to it. Life has got a hold of this planet. Now that tells us that if something happens and life gets eradicated on the surface, it doesn't mean that planet is dead. It may have life below the surface, all right? And so that might be the state we're talking about when we talk about Mars. Now, one of the next rovers that we landed was Perseverance. This is also in an ancient crater that was on the shoreline of the ancient ocean, for which the crater wall was broken down and the ocean poured into this area. But not only that, there was a wonderful feature, it's right here, of a river. And as this river, which is hundreds of miles upstream, carrying material as it scours the surface, and then hits still water in the crater, it dumps that and creates a delta. Now this delta is huge. It's more than 70 meters high, all right? Now we can go here on Earth and go to delta-like areas where ancient streams have poured into rivers and drop material, and we find plenty of evidence of past life. So by having this rover land in this area and interrogate this area, we hope to bring back material, because it is a sampler. This is coring rock, coring these sediments, putting them in tubes, and then we're planning to pick these tubes up and bring them back this decade. We're working hard on how to do that. And then look for, in the rock record, life. Now, why does that? Well, on Earth, we know there's like 5,700 plus minerals. And more than 330 of them can only be created by dead life. All right? So by looking at the rock record and looking at the mineralogy, it's going to give us an indication of whether there was life there in the past. And that indeed is the hope. And the only way we're going to do that is bring the samples back. And here's the architecture that we've been talking about, and that is we land on this left side a capsule. That capsule has a rocket, okay, called the Mars Ascent Vehicle. Then a fetch rover could be landed with it, or Perseverance brings sample over, load the rocket is assembled, goes up, drops the samples off in space, orbiting Mars, and then a spacecraft comes and snatches it and brings it back to Earth. Sounds neat, huh? Sounds like a few miracles in there. But that's what we're planning to do. All right, here is the North Polar Cap. And here's where we are with the sun's brightness, as we've shown before. And what's interesting about that is when we look at this spectrally, it's CO2, it's dry ice, CO2 snow, all right? But underneath that CO2 snow is water. And so our radars tell us this huge area, you know, here's a kilometer. Okay, so some of this is more than a kilometer high. And then you can see it's more than 1,000 kilometers in width, contains an enormous amount of water. In fact, what it contains is about 1/7 of the ancient ocean. Now, over time, what's going to happen is it's going to heat up. The CO2 will sublimate. The obliquity of this planet will move down. This will become more and more heated because it will be bathed in the sunlight. A new pole will be established. And then the hope is the water pours out and we end up with water on the surface of Mars again. Okay? So let's see what's happened to Mars. We believe Mars was a blue planet early on, plenty of indication of that, as I mentioned. It's popped out into the too cold area, but over time, as the sun heats up, it will release the frozen water, change the dynamics of the planet, and it may become habitable again. All right? So once again, when we look for exoplanets, even those that are Mars-sized, we got to know what evolutionary state they are in. Now, for the longest time, what we thought, these are planetary scientists, is there's an area called the snow line. Okay, so here it is on this graph. There's the sun as it evolves. And then you see Mercury, Venus, Earth, there it is, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Okay, and the snow line. So what's the snow line? Let's say you had an ice cube at Pluto. It's going to stay ice. And you move it closer and closer to the sun. How close can you get to the sun before the heat from the sun will sublimate the ice? In other words, break those bonds and have it go from solid right into vapor. That location is called the snow line. So for the longest, and where that snow line is, it's in the asteroid belt. It's beyond Mars. And so for the longest time, planetary scientists were really dubious about the state of water in the outer part of the solar system, okay? Okay, because anything beyond the snow line, that water gotta be frozen, right? Nope. Boy, were we wrong. What we've uncovered in the last 15 to 20 years are more and more moons that are out there that are getting energy, not from the sun, but from the giant planets they orbit. And so now we call those ocean worlds. And we have a whole new approach on how we're going to interrogate these ocean worlds. Now, why are these ocean worlds important? Well, once again, if we think water is where life could have started and migrated to land, or through a variety of processes in the ocean, which we are trying to feather out based on what we know about our Earth, create more and more complex life, which must be the case because we've got everything from whales to small crustaceans floating around and living and breathing in the ocean, then what's happening on these bodies we just really got to know about. So let's go to Jupiter and look at the moons. Here are the 4 big Galilean moons, all right? Callisto, Ganymede, Europa, and Io. Guess what? These were all made at the same time, and boy, do they look different. How come they look so different? Their evolution has been different, okay? Ganymede is just cratered all over the place. Each of these had ice shells. Io had an ice shell, but it's so close to Jupiter that ice shell has literally melted. It has more than 100 volcanoes on it at any one time. This is data from Juno, looking in the infrared, and all these spots you see are volcanoes. And that comes from tidal heating. That comes from orbiting Jupiter, where in an elliptical orbit. So at one phase, it's close to Jupiter. Jupiter squeezes it, and then as it moves to the other end of its orbit, it's further away, and it releases it. And so this motion, this tidal force from a huge body like Jupiter, which is 300 times the mass of our own planet, okay, 300 Earth masses, is just squeezing that body and turning it inside out. Every 80 years, you're going to need a new Google map on Io, okay? So its ice shell is gone. Europa's got an ice shell. Ganymede's got an ice shell. Callisto's got an ice shell. But the difference between Europa and Ganymede and Callisto is they're further away, and therefore the tidal forces are less. Now, Europa moves around Jupiter every 3.5 or 3.8 days, somewhere around in there. So every day and a half, it goes through this squeeze cycle, okay? And so what, is that enough heat to get rid of the ice shell? No, but it's just enough heat to melt part of the ice, but keep an icy crust. And so we believe Europa is in a habitable zone and may even be in a habitable state. We have a mission going there now to determine if it's really in a habitable state, because looks like it's got all the right stuff in it, and it's got a huge ocean for which life may exist. And that life actually may be complex because it's been this way for billions of years, okay? Ganymede, which is further away, has less stress on it, has an underground ocean, but that ocean has been communicating to the surface just like Europa. We don't see any craters on Europa. Europa should look like Callisto. Where did the craters go? The ocean is communicating to the surface. We see ice tectonics going on where one plate is going underneath another. It's a fabulous world that looks so much like the Earth in many ways in terms of the processes, and yet we don't know whether it has life in the ocean or not. Ganymede has an ocean that's just deeper, but it has communicated to the surface. That's why neither one of those bodies look like Callisto. So once again, Europa, no craters. Looks like it's got all the right stuff. It's got this ocean. It's got all the right kind of stuff, plenty of carbon, plenty of oxygen, all kinds of good stuff on it. We don't know if it's got every one of those things, but we'd like to find out. And it's got twice the amount of water that the Earth has on its surface, in its ocean. Now, one thing we think it has are hydrothermal vents. Now, why do we think that? Well, if you can imagine Io, and you look at Io and you see all these volcanoes, well, those are all caused by tidal forces. So if you're further away and you actually have an ice shell, you still have heat to dissipate. And more than likely, what's heating this ice and creating the underground ocean are hydrothermal vents. Now, hydrothermal vents here on Earth were discovered in 1978, and we've been to several hundred of them, okay? And each and every one of them are teeming with life, okay? So that means that Europa is a fantastic world where life might exist. As we continue on, here's Saturn. It has a fabulous moon called Enceladus. Enceladus has got plumes. Cassini flew through the plumes. And as it flew through the plumes, it was also hit by dust. And that dust is small particles that are flowing out of these hydrothermal vents, making their way up and coming out of these geysers. And then we hit it. So that's why we also know that Enceladus may have the right conditions for life. So it has all the best features, just like Europa does. Now, here's another fabulous moon. It's called Titan. Titan has an atmosphere, it's twice the atmospheric pressure of Earth. That atmosphere is dominated by nitrogen. and it has a whole series of trace gases in it. This moon is bigger than the planet Mercury. And if it wasn't orbiting Saturn, it was orbiting the sun, the astronomers would be forced to call it a planet. Yeah, they'd be forced to call it a planet. Now, what's really great about Titan, it is the only other body in the solar system that has liquid on its surface. And here's an ocean. It's a huge sea. Well, it's a sea, rather. Actually, this is Mare Kraken. It's bigger than our own Black Sea. But it's not water. It's liquid methane. It's that cold. Where methane we have here on Earth is a gas. If it gets too cold, becomes a liquid. All right? Right now, it's raining methane. They're coming down in big drops in the southern hemisphere of Titan because it has a methane cycle. Evaporation, transport, rain. Okay? Now, why is this so exciting? It's so exciting because it is potentially a different solvent, all right? And therefore, if we want to look for life that's not like us, this is the place, and it's just down the block. All right? Ocean worlds, we now have really looked at the moons of these giant planets in ways that are tremendously exciting. We now have a completely different paradigm. We should be looking for these moons of planets, and particularly the giant planets, to determine if there's life on them. And over the next 10 years, as we look through these, we'll discover all kinds of fantastic stuff. Now, tomorrow, we're going to talk a lot about exoplanets. So I'm just going to touch very, very, very briefly on taking what we know about our own solar system and cast that into some of the exoplanets. Now, one of my favorite exoplanet telescopes is this one. It's called Kepler. Kepler took a look at the sky and looked at 120,000 stars all at once. How cool is that? And all it did was measure its intensity, okay? Well, what happens is that light changes every once in a while. Could get brighter, could get dimmer. But when that pattern is nice and steady, goes down, and then goes back up to that same level, we know it was transited. Something moved in front of it. And that can be determined by that light curve. How deep, how long, tells us how big that planet is and how far away it is. Okay? And Kepler found thousands of planets. Now, I always thought, okay, the planet that's most out there, if there's ever going to be, find planets out there, what would I expect? Well, I would expect big Jupiters be all over the place, okay? Turns out that's not true. In fact, here is the number of planets, and this has now been normalized. This is what we think the basic topography of planet size looks like in the galaxy. So you have Mars-sized, Earth-sized, super-Earth, sub-Neptunes, and then you have the big planets, and Jupiter's down here at hardly anything. It's about as often as Earth-sized planets. And the planet that's out there the most are super-Earths. Now, we don't even have a super-Earth. What is that all about? Well, these super-Earths are bigger than our Earth and more massive. Now, it turns out they're not hugely bigger because they're terrestrial planets. They just have more mass. Now, that may mean, here's just a cutaway of what they could be. They could have a lot more soils, or they could have an extended ocean, okay, and an atmosphere that we can't quite determine exactly where the surface of that planet is. But now when we look into space, particularly with our wonderful telescopes, like JWST, we have an opportunity to look at the atmospheres. So we have some Rosetta Stones of atmospheres, okay? We have Rosetta Stones of the Earth atmosphere. We have Venus's atmosphere now because of our evolutionary models, Mars's atmospheres. And now we have a nice set of things that we can look at. And JWST is designed to take a good look at a particular wavelength that has some really great things in it. It has an opportunity to look for water. It has an opportunity to look for CO2 and even methane. Okay? So tomorrow we'll hear about where they are with that. Be very exciting. I hope you all come. But we also need to look for technosignatures. Okay? Are there signs of intelligent life on those planets? Maybe we can find, I don't know, CFCs or something, right? That's a joke. CFCs, of course, destroyed our ozone. We thought we were smart at the time generating them, but we realized that is a climate disaster in the making. So we no longer generate CFCs, okay. Chlorofluorocarbons, okay. So chlorine, the C there, was destroying ozone in Venus, and that's why we know CFCs are the culprits here on Earth, because we made those observations at Venus. Comparative planetology is incredibly important for us to understand how the Earth got the way it is and what its evolutionary track is. Okay? We have wonderful opportunities because we can look at those planets. I want to see if there's lights on the far side. What kind of spectrum do we get when the planet is black looking at us? When it's lit, are there trace gases? What are the land patterns? Can we determine ocean from land? And the answer is yes, we've done that with Earth. I had one of our spacecraft towards the end of its life, very far away from Earth, look at the Earth and get a spectrum of it. And as it sat there and stared at that planet, Earth, that spectrum changed. And it changed based on the percentage of ocean and land that it saw. And then all of a sudden, a huge change occurred. We thought, what the heck happened? Well, the moon moved in front of us. Okay? So now we have tools in the spectrum to look at that can tell us about land, tell us about oceans, and even if they have moons. That is really exciting because of our moon's help. Maybe those planets are also getting help. Bottom line on exoplanets are we now know there are more planets orbiting stars than there are stars in our Milky Way. All right? And so the search for life, as I close the box of the secrets, I've told you everything I know about them, tells us we're in a really exciting environment scientifically, because I think in your lifetime we will answer the question, are we alone? We haven't found life beyond Earth yet, but I think that's in our future. And I think that, so now I'm going to give you a personal story. I think the answer is yes. And there's plenty of life out there. And so we're really in for a treat. Thank you very much. We have time for some questions.
Yes.
All right.
Thank you very much.
Shall we sit down?
Yes, we sit
All right,
down.
let's do that.
You think on Europa there is life, or which, for example?
Yeah. So right now I'm writing a paper with several colleagues, and it's on Europa, and it starts from a different premise. All the scientists are going, well, we got to study Europa and determine if it has life by looking at its current signatures and look for this and look for that, and then that'll move us along to tell us, oh yeah, okay, it's in a habitable state, and then that'll move us along, you know, and they're creeping up on the life question from no life. So the title of this paper is really all about, there's life in the ocean of Europa, what does it look like and how has it evolved, okay? So planetary science-wise, I can do crazy things like that because I'm at the end of my career. You know, I have to turn in my planetary science library card because that's kind of an approach we don't take. But I think the conditions are such that it's just a fabulous body to explore. And the Europa Clipper is going to make many of those measurements. In fact, it's designed to see the plumes. We know plumes are occurring in Europa, okay? Now, when you compare that to Enceladus, we saw the plumes with Cassini. The plumes were, you know, go up 150, 200 kilometers. I mean, they're huge. Very hard to see on Europa. And why is that? Well, Enceladus is only 300 kilometers. It doesn't have a lot of gravity. Europa is this big as the moon. It's got plenty of gravity. So as you heat the water, it's only going to go so high. But all you have to do is you have to recognize there's hardly any craters on it, so it had to be resurfaced. We see subduction going on, okay, which circulates complex material that's being created because that surface being bombarded by the Jovian radiation belt, and all that stuff comes into the ocean, and it oxidizes the ocean. There's plenty of oxygen percolating in that area, and it's got to have hydrothermal vents. And it's been that way for a long time. I mean, what does life look like? Does it have eyes? Is it complex? And so you take an understanding of the evolutionary biology here on Earth, and you just apply it to Europa. So I think we're in for a treat.
Okay, so yeah, I'm looking forward to it.
I'll send you a copy.
So, but question concerning the moon. On the moon, we have water on the polar caps. Do you think there was possibly life too, or it was just?
No, I don't think it had the time. But you're right. We now know there's water in permanently shadowed craters. The axis of the moon is 1.5 degrees tilt, so the obliquity is hardly anything. All right, so that means there's areas that have been bombarded, huge holes that have been created, and then if you have volatiles like water coming to the moon and then precipitating out, like snowing out on the moon because it had an atmosphere, okay, over tens of millions of years, it's not going to go anywhere. There's no energy to sublimate it. It's colder in some of these areas than the surface of Pluto, where there's plenty of frozen water on Pluto. But not only that, is the magnetic field connections from Earth to the moon, as I showed in the one figure, allow a highway of evaporated Earth atmosphere to flow down those field lines and then snow out into the permanently shadowed regions. So I think it has early Earth atmosphere in it. It has early comet and asteroidal organic material. It has water from its own atmosphere along with other volatiles. And it actually has a water cycle right now, believe it or not, okay? So what does that water cycle look like? Well, the moon has water in it, just like the Earth does, and the moon and the Earth were created, at the same time. That theory is now more than 15 years old and is really held up. It's called the giant impact hypothesis. But it also gets pelted by micrometeors. We aren't, because our atmosphere just absorbs all that stuff. 100 tons of meteoric material hit the Earth every day, all right? And then it is either falls all the way down to the Earth or ends up burning up, become part of our atmosphere. And so consequently, these micrometeors that are hitting the moon, because it has no atmosphere, that shock wave liberates water. And so that water then comes out, and then it forms a big cloud around the moon and then migrates to the poles if it's not ionized by the sun and then swept away by the solar wind. That also happens. So that water cycle has been going for 3 billion years. So we need to go in these areas from a scientific perspective and core them. Get a core, an ice core. We go to Greenland and get a core, or we go to the Antarctic and get a core, and we look at those cores and it tells us the history of the Earth, okay? There's some fabulous things that come out of our own ice core. So by coring these areas and bringing them out, and I think only humans are really going to be able to do that the way we want it to be done. That's going to give us an enhanced understanding of the early Earth atmosphere and the early moon atmosphere and how these two have evolved, let alone then using those volatiles for a variety of things like breathing. You can separate the water into oxygen and hydrogen. You breathe the oxygen. Rocket fuel, you can use that for that. And, water's water. Even on the moon, it's still H2O, and you can drink it. This will be moon water soon enough.
Okay, so let's have some questions from the audience. And you wait for a microphone, yes?
Yeah. First, thank you for a really exciting talk.
Thank
It's
you.
great. Of the hundreds of exoplanets that you mentioned, how many of them are in solar systems that are, let's say, 3 or 4 billion years old to give time for life to be complex?
So there are all kinds of ages. One of the ones that JWST in particular is looking at is a star called TRAPPIST-1. Now, it's a different kind of star than ours. It's a smaller star, and that has advantages in that it can live at a certain intensity for longer periods of time. And therefore, it has an opportunity to maintain planets in a habitable state for long periods of time. It also has some detracting things about it. But there are 7 planets in that system. And so JWST is looking at them, although it's 7 billion years old, not 4.6, okay? This brings up another big question that we might be able to take a hint at by looking at the lifetime of species here on Earth, all right? What is the average lifetime species, okay? So you got trilobites, you got dinosaurs. Dinosaurs live 260 million years plus. You know, you got all kinds of life that come and go. Well, what's the average? Well, when I asked biologists and anthropologists, you know, what do we know about that? They come up with maybe 10 million years. Now, humans are only a couple million years old. It'd be great to think we could live for 10 billion or 10 million.
Let's
Sorry,
not get
10
carried away.
million. But I believe we can do better. Now, why is that? We are the first species on this planet that knows it can become extinct. Really? Why isn't that important to know? All right? And we know the processes that can kill us, okay? Everything from near-Earth objects to evolution of the sun to, you know, our nuclear problems, nuclear war, climate change, all the existential threats. We're on to that. And we may not be managing it perfectly. Okay, but we know we should be working that, all right? We're also the first species that had the opportunity to leave the gravitational bounds of this Earth, explore the solar system. In return, we're also pretty much the only species that can take care of other species. Now, there's symbiotic relationships, but I mean really have a concern about life that's not just us. You know, there's a lot of talk about us being in the 6th extinction. You know, I talked about 5 extinctions, but maybe we're in the 6th extinction right now. And what should we be doing about it, okay? These are all really important topics that we have to get involved in. We have to understand them more. And then we have to act on that result if we're going to live beyond the 10 million years. I would like to think we could make it 1 billion years. But in 800 million years, we'll have enough energy from the sun that we will look like Venus. Okay? Now, that's a long ways away, but we have the ability to do something about that. We can create a shield that reflects light, and we can put it at a certain location. Mathematically, we know what that is. Thank you, Ed and others that have done this. And that's at a Lagrangian point, and block some of the light and climate engineer us into a continual habitability. And we can terraform Mars. I mean, heck, we're doing a great job terraforming the Earth. Why, you know? So, I mean, there's a bunch of things that we can do, you know? And so we should be doing those, all of those, and more. Hope that answered your question.
Okay, so I think we, is there one more question and then, oh, over there, yeah, please.
Just what is your feeling about time? Without time travel, the information we're getting is old. So what are the implications for this information?
Okay, so I liked Interstellar too. You you know, but, and how I approach, you know, I was also the head consultant on the movie The Martian. And so I love science fiction in many ways. Right now to me, that's science fiction. We got a lot to do before we really have opportunity to mess with time. Although there is relativistic effects that we know about, but I mean, you're really talking about time travel is to me real science fiction. Now, relative to that, let me say one other thing. Do you have a cell phone?
Mhm.
Yeah, mine's put away. I'm old enough that I watched the original Star Trek. And on that very first episode, Captain Kirk landed on the surface and he called Scotty in the spaceship that was orbiting the Earth. I was gobsmacked with that idea, okay? That's fantastic, okay? But I have to tell you, with my own cell phone, today, a couple years ago, I had an opportunity to call Jessica Meir on the International Space Station. I had her number, and she had to have, she was working, and there was a little time slot. I couldn't make it, but I could have called her and talked to her on my cell phone. Okay. To me, I was gobsmacked with that idea. So that science, pure science fiction in my lifetime became a reality. Okay. So although time travel to me is still science fiction, and I don't have the ability to make it happen, but maybe somebody out there does. But I doubt it.
Okay, so let's thank Jim again for this wonderful lecture.
Thank you very much. Thank you. Thank you. Thank you so much. Thank you.